This video contains the solutions for numbers 1 through 8, first two pages front and back of your Physics C practice test. Number 1, if we have an object that is moving in a straight line, so only one dimension, there's only one distance dimension, over time with positive acceleration. Well, if it wasn't, this is a graph, if it was not moving at all, right? In other words, it has the same position, same position, same position, but as time moves this way, it just is in the same place. This is a graph of something that has, let's say, a constant slope, so that would be something with a constant velocity. This would be a constant negative velocity. This is a constant positive acceleration, and this is a constant negative acceleration. We do have to be careful that make sure that all of these are the same. It's possible that they could give some d graphs and some velocity graphs and so on. So if this were an acceleration graph, that would be the correct answer, but they're all position graphs. So the correct answer is D. Number 2, a ball is thrown straight up from a point that is 2 meters above the ground. Here's the ground, so we're throwing it from here. That's 2 meters. And reaches a maximum height 3 meters above its starting point. So from here to here is 3 meters, and then goes down 5 meters to the ground. So its displacement is, well, it started here and ended up here, so 2 meters in the down direction, or 2 meters below, as they said. That's D. Number 3, what do acceleration and velocity have in common? Let's go through the answers here. Both are scalars? Well, no, they're both vectors, in fact, and there's that. That is the correct answer. But let's go through the other ones and see why they are wrong. Both are measured in units of distance divided by time. Well, that's not true. Acceleration is distance divided by time squared, and velocity is distance divided by time. So those are both wrong because they only describe one or the other, and they are different names for the same quantity. Come on, that's ridiculous. Well, we could say, like, how would you describe, like, what is acceleration? It's the rate at which velocity changes, right? Meters per second. Number 4, 2 projectiles are launched with the same initial speed from the same location, one at a 30-degree angle and the other at a 60-degree angle with the horizontal. They land at the same height at which they were launched, so just like from ground to ground. If air resistance is negligible, how do the projectiles' respective maximum heights and times in the air compare with each other? Well, let's make a little picture, I think. And we want to write out a little bit of work for this one. So number 4, we've got a projectile launched at 60 degrees and another one that's launched at 30 degrees with the same velocity. Well, the only thing that the height depends on is the vertical component of the initial velocity, right? So we broke that up into its 2 components. So the bigger this part is, the higher it will go, and the higher it goes, the longer it's in the air, right? So I think that this one, because it's got more of a vertical component, they didn't ask anything about how far it would go. That would be a different question. The greater vertical velocity here means that it's going to be in the air longer. Exactly how much longer? Well, it doesn't matter. We don't need to know that. So I think that if this is the height of the 60, will be greater than the height of the 30-degree one. And for exactly the same reason, the higher it goes, I mean, it's the same acceleration that's acting on these things. So higher means in the air longer. So the time is also greater for that one. And that looks like answer choice E. They have their inequalities the other way around as less thans, but that corresponds to answer choice E. Number 5, we have an object of mass 100 kilograms is initially at rest on a horizontal frictionless surface. Time t0, a horizontal force of 10 newtons is applied to the object for 1 second and then removed. Which of the following is true of the object at time 2 seconds? Let's see. So at time 0 up to time 1, there's a force acting on it, and then it's removed. So in other words, at t equals 2, there's no more force acting on it. So which of the following is still true if it's still on its frictionless surface? Is it at the same position since a force of 10 newtons is not large enough to move such a massive object? Well, that's not true. 10 newtons is a pretty small force, about 2 pounds or so. But 100 kilograms, it doesn't matter if it's on a frictionless surface. It might accelerate very gradually, but if it's on a frictionless surface, it could be 1,000,000 kilograms or 1,000,000,000 kilograms or the entire Earth. If it were on a frictionless surface, 10 newtons will cause an acceleration. So that's not true. It is moving with a constant non-zero acceleration. Well, I think we took the force away. So if the force is gone, then the acceleration is gone. So it's not accelerating at all. And that eliminates B and C, right? Because at this point, there's no force acting on it. No net force, right? There are forces. If you wanted to draw a free body diagram, it's moving with a velocity in this direction, but the forces on it are gravity and the normal force. No force in either of those directions, so the net force is 0. It's moving at a constant speed. Well, that makes sense because there's no acceleration, no force, so it would be moving at a constant speed. And then to make sure that E is wrong, it has come to rest some distance away. Well, if there were friction, then it would come to rest, but if it's still on a frictionless surface, it's going to keep going. So the correct answer is D. Number 6. We have here several forces. This is another Newton's second law question. Several forces act on an object, but the object is in equilibrium. So much like this object was right here. Which of the following statements about the object must be true? Well, vocabulary here. Something can be in equilibrium, or something is in equilibrium when the net force on it is 0. Now that can be true when it's moving at a constant velocity, like this was, or when it's in static equilibrium, when it's not moving. So it must have a constant velocity for the net force to be 0 and for it to be in equilibrium. But of course 0 is also a constant velocity. It doesn't have to be stationary. So if the net force is 0, does it have 0 acceleration? You bet. No net force, no acceleration. Is the net force acting on it 0? Yeah, that's the definition of equilibrium. Is it at rest? Well, maybe. It could be. Is it moving with a constant velocity? Well, that's the other option. But neither of those two must be true, right? It would either be at rest or moving with a constant velocity. But in either one of those cases, we would still have equilibrium. So the correct answer is A, 1 and 2. And if you determine that those two have to be true, that's the only answer choice that includes both of those. So maybe that kind of nudges you in the right direction, even if you thought at first that it would have to be at rest. So the correct answer is A. Oops, I think this video is going to be upside down. Why does that happen? In number 7, a rock is thrown from the edge of a cliff with an initial velocity v sub 0 at an angle theta with the horizontal as shown above. Point P is the highest point in the rock's trajectory, and Q is level with the starting point. And we're going to neglect air resistance. Which of the following correctly describes the horizontal and vertical speeds and the acceleration of the rock at point P? Well, let's see, the acceleration anywhere is going to be g down. So let's see, acceleration has to be g. That automatically eliminates those. There's certainly not 0 acceleration. The vertical speed here, because it's reached the top here, just for an instant as it goes up and then down again, the vertical component would be 0. The velocity is tangent to the path, so velocity is all horizontal right here. So let's see, we need a vertical speed of 0, so that eliminates Does that eliminate another one? What did we eliminate so far? I guess we can eliminate D now, right? Because that's not. So what are we down to now? A and B. And it doesn't have a zero horizontal speed. Its horizontal speed is constant. It's that component, which is the cosine component of the initial velocity, and that would be constant throughout. So the correct answer is A. Number 8, which of the following correctly describes the horizontal and vertical speeds and the acceleration of the rock at point Q? Well, the acceleration is g always, so let's get rid of C and E. And I think it has both a horizontal and a vertical speed, and in fact those are exactly the same as they were here, because as it returns to that same point, it has this velocity. So if it had the horizontal velocity is constant, that's v cosine theta, and at the same height here it would regain the same velocity that it had. The vertical component would be the same as when it was launched, just in the opposite direction. So they would be v cosine theta and v sine theta, and that's answer choice D. Sorry about that being upside down. I'll try to fix that in the next one.